So these are going to be my solutions to the 2019 AP Chemistry FRQ response for response question number 1. Quick disclaimer, it's likely that I make a small mistake because the scoring guidelines haven't been released yet, so I can't formally check my answers, but I'm very confident that my answers are at least mostly right. So take what I do with a grain of salt. So number 1, the first part of it says the compound urea is widely used in chemical fertilizers, and it gives you the complete Lewis electron dot diagram for that molecule. And part A says identify the hybridization of the valence orbitals of the carbon atom and the urea molecule. So what you need to look at here is the regions of electron density, the number of them, and there's 3. Many might think there's 4 because it's a double bond, but double bonds are their own region. So there's only 3 here, so the hybridization is simply sp2. The steric number here, the addition of the exponent should equal the total number of electron density regions, and it does 1 plus 2 equals 3. And that's your answer for part B. It doesn't ask you to justify at all, which is helpful. Part B says urea has a high solubility in water due in part to its ability to form hydrogen bonds, and it asks you to draw one dashed line to indicate a possible location of a hydrogen bond between a water molecule here, or one of these water molecules, and the urea molecule. So a hydrogen bond will occur between an atom's hydrogen. It's an intermolecular force, so it's not gonna, or intermolecular force, so it's not gonna happen between a molecule. It can happen between many molecules of the same substance, but it's not gonna happen in a molecule itself. It'll happen between 2 molecules that are nearby each other, between a hydrogen and either a fluorine, an oxygen, or nitrogen. What I put was the bond here. This is a oxygen, this is a hydrogen. It says to only draw one dashed line. Really, you could put it here, you could put it here, but I'm not sure about putting it here because I'm not completely sure this is right, but what I'm thinking is the repellent force between these 2 positively charged particles is going to significantly weaken, if not overcome completely, the hydrogen bond between this hydrogen and this oxygen. So this may not be a safe option, but I really can't tell you until the scoring guidelines come out. It doesn't ask you to justify again, so that's your answer for part B. And the dissolution of urea is represented by the equation above. This chemical reaction here. The student determines that 5.39 grams of urea can dissolve in water to make 5 milliliters of a saturated solution at 20 degrees Celsius. So this is as simple as converting your grams to moles. So 5.39 grams for every 60 grams, there's 1 mole, and that'll come out to 0.097 moles. And then you divide your amount of moles by the total volume of the solution. Don't forget to convert to liters, and you'll get 17.9 moles per liter. Now, formally, this is for part C, by the way. Formally, you put that as molar, but the question specifically asks you for moles per liter. I don't think the graders will be very strict about that, but it is worth following the question just in case. So that's your answer for part C. Part D says the student determines the concentration of urea in a saturated solution at 25 degrees Celsius is 19.8 molar. Based on this information, is the dissolution of urea endothermic or exothermic? Justify your answer in terms of Le Chatelier's principle. So the best option here is to physically, in my opinion, put heat in this reaction. We're going to go with the wrong answer first just to showcase this better. So the first thing to notice is that temperature increased and the concentration increased. This concentration isn't the concentration of the solid reactant. That doesn't make sense per se, because concentration is a property of a solution, and the solid itself isn't a solution. If you wanted to describe the concentration, quote unquote, of a solid, you'd have to use density. But it doesn't ask you about density. So temperature goes up in this case. So in an exothermic reaction, when temperature goes up, right, the reaction will shift to the left, just like any normal other Le Chatelier's principle problem. It'll go to the side to alleviate that addition of heat, which means that the concentration would decrease if it were exothermic, and the concentration clearly increases from 17.9 to 19.8. So this is wrong. It's endothermic, and the way you justify that is the concentration increasing corresponds with the reaction shifting to the right towards the products, and because the reaction shifts right as temperature increases, the reaction is endothermic. And that's it for Part D. Part E says the equipment shown above is provided so that the student can determine the value of the molar heat of solution for urea. Knowing that the specific heat of the solution is 4.18 joules per gram degree Celsius, list the specific measurements that are required to be made during the experiment. So, Part E says, it doesn't ask you to actually go over the experimental procedure, but what I did specifically on my FRQ, I remember this was, I wrote out the procedure, listed the measurements that I made in that procedure in a separate part, and then crossed out the entire experimental procedure. This is a waste of time, I agree, but I'm a fast worker, so I can afford it. So just for me, that was the easiest way to not forget any measurements. So I'm going to go over the experimental procedure for this. So what you do, right, is first you have to measure the amount of water that you're dissolving urea in, right? And the best way to do that would be measuring the polystyrene cup without the water in it, and then measuring it with the water in it, and then subtracting those two masses to get the mass of the water. So it's two measurements, the mass of the polystyrene cup without the water and the mass with the water. And then after that, you need to measure or somehow find a value for the amount of moles that you dissolved in the water of urea. And the easiest way to do that, or the best way to do that, is to measure the mass of the bottle with the urea in it. And then after you dump that in the water, set the bottle aside because you need to make the measurement very quickly of the change in temperature, right? So in order to find the amount of heat absorbed, in this case because it's endothermic, not released, you need to know the change of temperature, so you need to know the room temperature of the room that you're in and the final temperature of the solution after dissolving the urea in it. And then after that, you can measure the bottle without the urea to find the mass of the urea you use, convert urea to moles, and then find the heat released by using Q equals MCAT, because you have the change of temperature, you have the final temperature of the solution minus the initial temperature of the solution. Then you can divide that amount of heat by that amount of moles of urea dissolved, and then make that value positive because it's endothermic. And now you have the molar heat of the solution. It doesn't ask you to walk through this, but just walking through that better help me list what I need. So the mass of the cup without the water, the mass of the cup with the water, the mass of the bottle with the urea, the mass of the bottle without the urea, the room temperature, and the final temperature of the solution. Don't use variables like this. You may be able to get away with that, but just to be explicit about this, write mass of the cup without water. Obviously, you can write chemical formulas. Mass of the cup, physically writing out the English sentence. Mass of the cup, mass of the bottle, mass of the bottle again. And this is definitely explicit enough. It's just using M for variable. It's not very explicitly defined. So that's part E. And part F says the entropy change for the dissolution of urea is 70.1 joules per mole Kelvin at 25 degrees Celsius. Use the information in the table above. Calculate the absolute molar entropy of aqueous urea. So there's a formula in your formula sheet. Delta S is the absolute molar entropy of the products minus the absolute molar entropy of the reactants, the sum of both of those individually. And the products is just one, right? So the sum of one thing is just one thing, which is the molar entropy of aqueous urea. And the reactants is just that solid urea, you're given all these values, 70.1 right here, equals X, whatever you're trying to find, the molar entropy of aqueous urea, which is a product, minus 104.6, which is the value they give you here for solid urea. Solving for that will give you 175 joules per mole Kelvin. It's entropy value, the units of joules per mole Kelvin. And that's part F. Part G says, using particle level reasoning, explain why delta S is positive for the dissolution of urea in water. So this is essentially just explaining why an aqueous solution is going to have more entropy than that same solid, right? And this is simply because there's more disorder in the aqueous solution because the ions are more free to move around than the solid compound. And because the aqueous solution, which is the final part of it, which is the product of the reaction, the entropy of this will be greater than the entropy of the solid because of their states. Delta S is positive because delta S is final entropy minus initial entropy, and final entropy is greater than initial entropy, so delta S is going to be positive. And that should be good. Just make sure you actually include the particle level reasoning that the particles in the aqueous solution are more free to move around than in the solid compound form. Part H says, a student claims that delta S for the process contributes to the thermodynamic favorability of the dissolution of urea at 25 degrees Celsius. Use the thermodynamic information above to support the student's claim. So thermodynamic favorability means that delta G is less than 0. And that's also equal to delta H minus T delta S, which is less than 0 for this case. And the reason why delta S for the process contributes to the thermodynamic favorability is because delta S being positive makes this term more negative, which makes delta G more negative because you're essentially just subtracting a bigger and bigger number the more positive delta S gets. So delta S being positive makes delta G more negative, which makes the reaction more thermodynamically favorable. And I think that would set you for part H in terms of your explanation. I'd cite the actual equation just to be more mathematically rigorous about it. But yeah, that's it for question number 1.